So our speaker is Seok Hyun, and who is from Indiana University, Bloomington, and will be talking about Lozenge tilings of hexagon with vertical intrusion.
Yeah, thank you for the introduction. So as you can see from the title, my talk is about Lozenge tilings. I mean, originally, I would like to begin my talk with the plane partitions, but I figured out that 15 minutes is very short. So I decided to jump into the Lozenge tilings without saying anything about the plane partition. So first, I should say something about Lozenge and Lozenge tilings. So let me do that first. So I will assume that all of you know the triangular grid. It is on the slide, right? Then what is the lozenge? Lozenge is simply a union of two adjacent triangles that share an edge. And according to their orientation, there are three types of lozenges. I mean, on the slide and on the left, there is a left tilted lozenge and right tilted lozenge on the right, and a vertical lozenge at the center. So these are three types of lozenges that we are going to use. And then we will consider a region on a triangular grid. There are many ways to define it, but let me simply define it as a union of unit triangles. So on the slide, here is an example of region. And if you believe me, it consists of 56 unit triangles. So when a region is given on a triangular grid, what we are going to do is we will think about is lozenge tiling. Then what is a lozenge tiling? Given a region, a lozenge tiling is just a collection of lozenges that cover the region without any gaps or overlappings. So on the slide, I provide an example of lozenge tiling of the region that we have seen in the previous slide. I mean, this region consists of 56 unit triangles, so the lozenge tiling of it should consist of 28 unit lozenges. So now I hope all of you know at least what the lozenge tiling is. So when a region R is given on a triangular grid, there is one natural question that comes up. How many lozenge tilings does this region have? So this is the enumeration question, and this is the question that I'm going to talk about. And for the rest of this talk, we will set some notation. Let M of R be the number of lozenge tiling of the region R. In general, this is a very hard question. So we will focus on some region which is relatively well known. And the region which is relatively well known is a hexagonal region. So we now jump into the lozenge tiling of a hexagon. So let H sub A, B, and C be the hexagon of side length A, B, and C clockwise from the top. So what I mean is this is A, B, C, and then A, B, C. So in the example on the slide, the side lengths are 1, 2, 2, 1, 2, 2. So this is H sub 1, 2, and 2. And on the bottom, I provided 6 lozenge tilings of this region. And in fact, you can check that these are all the lozenge tilings of this region. Then using our notation, we can say that M of this hexagon is equal to 6. But I told you that this question is already well known, right? In fact, this problem was proved more than 100 years ago by MacMahon. I should mention that, in fact, the statement that he had proved is not this. Instead, he enumerated the number of plane partitions with some restrictions. But it turns out that what he had proved is equivalent to this statement. So that's the reason why I put lozenge tiling version of the MacMahon's theorem. And what is the theorem? The theorem says that the number of lozenge tiling of this hexagonal region is given by this nice triple product formula. So for example, if you replace A by 1, B and C by 2, you should get 6 because we enumerate these lozenge tilings in the previous slide. So this theorem is very general and beautiful enough, but mathematicians do not stop here. So in 1996, James Propp presented 20 open problems in enumeration of matching at MSRI. And among 20 problems, the problem number 1 is the following. So we have this hexagon. And then what we are going to do is we will cover the central location by a lozenge. And then what the problem is asking is that this ratio is exactly 1/3. Maybe it is not clear, so I provide some example in the next slide. So on the left, we have a hexagon, right? This is a hexagon of side lengths 6, 5, 5, 6, 5, and 5. And on the right, I drew the same hexagon, right? 6, 5, 5. But there's one difference. I delete the central lozenge here. I remove it. So this one is removed. Then by using some computer's help, we can enumerate the number of lozenge tilings of these two regions, and the number of lozenge tiling of the region on the left, the hexagonal region, is this, and the number of lozenge tiling of the right region is this. And one can check that the ratio of these two numbers is 1/3. So there should be some reason why it is true, right? So many people try to solve this problem, and many people were succeeded. So here are some names of the authors who proved and generalized this Propp's problem. And I want to focus on Fulmek and Kranttenthaler's theorem and their conjecture in the same paper. So Fulmek and Kranttenthaler, what they have proved is more general than the original problem. So here's very complicated expressions, right? And they say that the ratio of these two numbers is exactly this. But I want to point out that denominator is already known by the MacMahon's formula. So in fact, what they have figured out is the formula for this region. But I should specify what this region is, right? So I prepare a picture on the next slide. So let's see it. So let's see the leftmost picture. On the leftmost picture, the top side length 2a is equal to 4, and this oblique side is b, which is 5. And then what we do is we focus on the vertical symmetry axis. And then we label the lozenges on the vertical symmetry axis by 1, 2, 3, 4, 5. So the leftmost picture is the one that I delete the topmost lozenge, right? And the second one, so in this case, d is equal to 1. And in the second picture, d is equal to 2 because we delete the second lozenges from the top, right? So this is the second, and d is equal to 3, d is equal to 4, d is equal to 5. So these are the examples of the regions that Fulmek and Kranttenthaler's theorem enumerate the number of lozenge tilings. But in the same paper, they also conjecture a similar statement. This is the conjecture that they pose on the same paper. So here's also very complicated expressions, right? And maybe some notations are not familiar with you, but here the definitions are provided. And on the left, it is again the ratio, right? And again, the denominator is also known by the MacMahon's formula. So in fact, what they conjectured is the number of lozenge tiling of this region. Then what is this region? So I will also provide some pictures of these regions. So again, the top side length, which is 2a, is equal to 4 in this case. And the oblique side length, which is b, is 5. And then instead of deleting a single lozenge, what they have done is they delete several lozenges. So in this case, they remove on the symmetry axis, they remove the single lozenge on the top, so D is equal to 1. And then on the second picture, they remove 2 of them. So D is 2, D is 3, and so on. So the conjecture of Fulmek and Kranttenthaler enumerate the number of lozenge tilings of such regions. But I call it conjecture, but I should not call it conjecture because the proof of this conjecture was provided in a paper of Seok and Kranttenthaler. But although it is not a conjecture, then one can try to generalize it, right? Then how can you generalize it? So going back to this picture, this conjecture can be formulated as follows. I call this line a vertical symmetry axis, but let me just call it a perpendicular bisector of the top side, because it is, right? And then from the vertical not vertical symmetry axis, but from this perpendicular bisector, what they have done is they removed several unit triangles on the top, right? So keeping this in our mind, what one can try is to consider a more general region with the same removal. So here are the regions that I care. So this is not a symmetric this is a general hexagon which does not have any symmetry, right? But what one can do is we consider another vertical symmetry axis, but perpendicular bisector of the top side. So they have the same length, right? And then I remove the several unit triangles, but even number of unit triangles. And then, so this side length is 6, this side length is 5, this side length is 8, and I remove 6 of them, and 6 over 2 is equal to 3. So the region on the left is denoted by H sub 658 semicolon 3. So first 3 numbers represent the length of the hexagon, and the last number represent the half of the number of unit triangles that I have removed. But the same idea can be applied when the side length of the top is odd. So we consider the vertical bisector. They have the same length, and I remove the even number of unit triangles. Then by same argument, I can call it this. 7, 5, 8 represent the side length, and 3 represent the depth of depth, or the number of 2 times the half of the number of unit triangles that I have removed. And here are some notations that are needed to understand the statement. And here is the theorem. So we have some complicated expression here or here. And again, denominator is known by MacMahon's formula. And same for this. So this theorem provides the number of lozenge tiling of this region and this region. Then how to prove it? How to prove such identity? The proof is inductive, and the inductive proof uses the following 2 recurrence relations. And these 2 recurrence relations can be obtained by using Kuo's graphical condensation. But I don't have enough time to explain what it is. So these are the idea of the proof. And these are some questions, but I think I don't have enough time, so let me skip. And here are some references that I have used. And thank you for listening. Oh, I have 1 minute left.
Thank you, Seok Hyun.
Yeah, you're welcome. Yeah.
I guess it's 20, and usually try to keep 5 minutes. But if you want, maybe one last comment, if you had one. Or...
maybe then. Right. Here are 2 questions, and one of the questions is why these numbers are so nice in the sense that each factor is linear. I mean, if you see the formula, there are many factors, and all the factors are linear in A, B, C, and D. I mean, although I prove it, I have no idea why it is the case. So this is one of my question. And second question is, I want to see the more simple and conceptual proof bit. As I told you, the proof is inductive, which means I should have guessed this formula. But hopefully I want to see a better proof, which can prove this without guessing this formula. So that's all comment that I have, yeah.
I had a question about your code. So to count the number of tilings,
Yeah.
you said you use computer system. Like, how hard is it and how expensive is it to actually?
Oh, right. That's a good question. In fact, there is a program called VexMax, which is written by David Wilson.
Okay.
So I mean, I can provide you a link of his website, because if you are familiar with Maple, then I think you can easily install it on your computer.
Okay.
So I have two questions. So first question is, do you know, do you have any results about enumerating lozenge tilings where some lozenges are missing, but not on the vertical symmetry axis, but rather on some other locations?
Right, from the perpendicular bisector of the top sides.
If not there, but somewhere else, and possibly of a different shape than the one you are enumerating in this one, and because you can rotate it, right? And the other question is there some? So I know. So is there a relation between as in, do your proofs involve the ASMs or six vertex models, or do you have some relation between these?
That's a good question. Yeah, I mean, lozenge tiling and ASMs are some good friend to each other, right? But unfortunately, my proof does not involve any ideas from six vertex model or ASM. Yeah. And I think your question is, if I understand correctly, can I move this hole's location, right?
Yeah.
But the thing is, my proof strongly used the fact that these are on this vertical line. So I told you that I made some recursive relation, right?
Mm-hmm.
And when I make that recurrence relation, I strongly use the fact that the holes are on this vertical line. But maybe maybe the number of lozenge tiling with with holes on other vertical axis may have a nice product formula, but at this point I have no idea how to prove it, because my proof does not apply for other cases.
Right, I see.
Yeah. I see. So do I answer your all questions?
Yeah. Thank you.
Yeah, you're welcome.
Okay, if there are no more questions, let's thank Seok Hyun again.